Okay, well, what I put up on the screen, up on the blackboard already is on the left-hand side of f of x. I circled an equal sign. There's a reason for that in a minute. Anyway, this is f of x naught. So what you have is some number that you know, which we label as x naught, x sub 0. And it's somewhere in the real line. I don't know if it's positive or negative or 0. Okay. And at that place, if I assume I can differentiate the function, this indicates the kth derivative, where k can go from, now, I already made a mistake, but I want you to see, if I put the f of x naught out here, that's a constant. I don't want to have another constant here, and so I would put 1 here, and I don't forget to put k up here. Okay, so first moral to the story, make sure you set the thing up right. Okay, get the notation right. If the notation's wrong, it's going to screw up everything, and you're doing it from the very beginning, and it's going to mess up every step. So when I have it like this, finally, when k is 1, I have just x minus x naught. That's like to the first power. When k is 2, it's squared. When k is 3, and so on. And we form what's called a power series. All right, that's an example of the situation where we list, instead of listing function things, we do the same thing, except instead of f something, we have a sub something. So this is a general thing for a power series. If we have a function for which we make the power series where we assign the a sub k to be the kth derivative at x naught over k factorial, if we do that, then we have what is called a Taylor series. So this thing over here is called a power series about x naught. This is a Taylor series about x naught. Okay. When you solve a differential equation, you will get a power series. Some power series are functions that you know. They are sines, cosines, exponential functions, logarithms, something. Most are not. But we have so far in the semester been doing ones where you come up with names we know. And so for those power series we've already solved, if we try to talk about the function, change it into a power series, that would have to do with making Taylor series. Now, what's the circle about around the equal sign? When I just make a power series by putting these things in for a, and by the way, a sub 0 would just be f of x sub 0. Okay, so if we have a power series and I have a function and I stick this stuff in there, I will get the right-hand side. But it doesn't mean that I get a number. In other words, the series might diverge. We've already learned from review that you have a power series and it converges in, so let's try different ones here. If I have a power series k factorial x to the k, like this series diverges everywhere except 0. Okay, so this particular series doesn't converge any place except 0. Any number you put here, no matter how small or how large, this does not mean anything. Okay, we write infinity, but it doesn't mean anything. So we can have a power series that only converges at one point. Okay, if you put 0 in here, you just get 1, obviously. Okay, so we assume that as long as I take some number rho, and as long as I stay inside that distance, when I write this, I try to find that distance. So if I stay inside it, I have convergence. So the x is somewhere inside an interval in which you assume or prove, depending on the circumstances, that the series with that number x stuck in it converges. As a bit of a review, we use a ratio test to try to find that out. And the ratio test will give us an open interval as long as it's not just one point. It will give us an open symmetric interval around which, if you pick any x in that area, you will get convergence. If you pick any x outside that interval, you'll get divergence. But you have to check the endpoints because the theory doesn't tell you about the endpoints. So you do the ratio test, which gives you an open interval, and then you test both endpoints of that interval to see if the interval of convergence is open, half open, or closed. Half open means open at one end and closed at the other end. Okay, those are the possibilities. Now, getting back to the equal sign here, but I can make up a series in which I stick these things into it. For example, suppose f of x is just x cubed. That's a polynomial, pretty simple one. That's x cubed. If somebody says, write down the Taylor series about 0, you say yes, because this is the Taylor series about 0. There is nothing to do. Or is it? Well, if I tried to see if this is it, I'd have to differentiate. Okay. Differentiate. Now, that's not 0, but we don't make up this thing from this thing exactly. There's a difference between f prime of x and f derivative of x naught, meaning after you differentiate, you do not leave it as x. We don't stick 3x squared into a formula. You evaluate at the place called x naught. So the thing we want to put into the formula would be whatever that is, and that's 0. So I'm going to make up the Taylor series, but the first thing is going to be 0. If I differentiate the power series again, I'll get 6x, but I don't care about that. I want to know what it is at 0, and it's 0. If I differentiate again, I will get x, I will get 6. And if I stick in this time, I'll get 6, because this time there is no x to go. And if I differentiate anymore, f sub k for k greater than 3 is going to be 0, because the derivative, in other words, the derivative at x is 0, so x not 0. So if I make up my power series from these things, the f of 0 is 0, f prime of 0 is 0 times x over 1 factorial, f double prime is 0 times x squared over 2 factorial, f triple prime is 6 x cubed over 3 factorial, and all the rest of them are 0. So if I try to make up a power series of x cubed, namely a Taylor series, what do I get? This 6 I got is going to be divided by 6, and so what I'm going to get? I'm going to get x cubed. In other words, a polynomial is already a power series. And it's already, if you write it as powers of x, it's already a Maclaurin series. So you can think of these infinite series as polynomials that just keep getting higher and higher and higher powers. you shouldn't use any mathematics on that idea, but in your mind, you can think about a series as just a really big polynomial in terms of the powers. Now, humans are notoriously bad at adding up stuff. And therefore, you don't think of just adding up x powers to infinity, you think about taking the limit of the sequence of partial sums. We take limits, we don't add up an infinite number of things. Okay, but to get back to this, you can make up a power series. Whether or not it adds up to f is a question. When it does, it's called analytic. Okay, and we will be dealing with analytic functions. It means the function has a convergent Taylor series in some neighborhood of the point in which you are expanding it. If I'm doing x minus x naught, we say we're expanding it in terms of x sub 0, okay? Now, analytic functions are best studied in complex variables, not real variables. What we'll be talking about is real analytic functions. And it has to do with convergent around some point, in this case 0. And that's what we're talking about, okay? So, if, just while I'm on that subject, this is actually in the next section beyond where we are here at the moment, but if I have a second order differential equation, let's say, and we've had things like this before. So I'm just making, didn't plan to say this, but sort of making this up here at the moment. If I have a solution of this, and if I have initial conditions, if I know y of, say, in this case, 0 is y naught and y sub 0 prime is, say 0 is y naught prime, let's say, okay. This tells me if I want to make up a Maclaurin series, that's when x is 0, x sub 0 is 0, okay? If I wanted to make one up, what does this tell me already? If I have a solution, let's say the solution's f. This says f of 0 is y naught, and it says f prime of 0 is y naught prime. What are those? Those are the first things. One of them is this one, and the next one is when k is 1, right? In other words, if I have a solution and initial conditions, the two first things are already known. And I can do, okay, so here's what I'm trying to get at here. If I try to make up here's a differential equation, don't know how to solve it, but I have initial conditions. I want to see if a function like this works. Okay, so when I look at what I got, I'm trying to make up this function f as a power series. The function f as a power series is, I'm just repeating it now, it's f of x0, but that, okay, if x0 is 0, that's just f of 0, and that's just y naught. So I already know the first term of the power series. Okay, I'm trying to find all of these things. The second comment here says I already know what it is. That's y naught prime times x. I already know it. And I have a second order equation. So I can solve the second equation. It's minus p of x, y of x, y prime of x, sorry, and minus q of x, y of x. So I've got a function, I've got an equation. If I just rewrite it, I got that. So what happens if I stick 0 in here? Y double prime of 0 is minus p of 0, y prime of 0 minus q of 0, y of 0. And the point is, I know what the function p is, I know what the function q is, Therefore, I know what P of 0 is, and I know what Q of 0 is, and I know what Y prime of 0 is, and I know what Y of 0 is. So what do I know? I know what Y double prime of 0 is. In other words, I can make up, I'm going to write it here and not write out all that stuff, but I found out what that is just by plugging in the 0. And so that would be x squared over 2 factorial. So I've already got the first 3 terms of an answer without having any idea what the answer is. It's a quadratic equation. This one's a known number, known number, known number. What's it look like? So it's going to look like this, or it's going to look like this. Polynomial, degree 2. So without solving the equation, I already got the first 3 terms of the Taylor expansion, which will be, if I have all of the terms, it will be the answer. So you might think, oh, this is easy. Well, it's not that easy. What's the third derivative? Well, I have a formula for the second derivative. I haven't solved for the formula, but if I assume I have a function, I can differentiate that because, well, if the P and the Q are differentiable, then I can do derivatives on this because I have products and differences, and I can figure out what the third derivative is. Stick in 0, get another number. So I can build a solution without knowing what the solution is. Now, I'm not sure that P and Q are differentiable. All we assumed in the last chapter was they are continuous. So I couldn't go much further with this if these are not differentiable. All right. So in the future, not right yet, in the future, we're going to be assuming that the P and the Q are themselves analytic, meaning they have all derivatives of every order, and the Taylor series or Maclaurin series converges for those functions. But that's getting ahead of ourselves. Okay. But I just thought it might interest you to see, we don't know anything about the solution, but if we want to make it a power series, we can do that. We can start doing it anyway. Okay, so that's actually in the next section, and we're not there yet, so I'll erase this and act like we don't know about that yet. Okay, so it's about time to do a problem, okay? And we already, the other day, looked at the problem y double prime. Remember, example 1 was y double prime plus y equals 0, I believe. Or was it y double prime minus y equals 0? It was example 1. I'm sure you guys studied the heck out of it, so you ought to know the answer to that. In one case, if I did it, I would get roots of plus or minus 1, and I would get exponential solutions, but that wasn't the one we got. We got solutions that were cosine and sine, if you remember. So example 1 was y double prime plus y equals 0. That gives us a characteristic equation of r squared plus 1 equals 0, which gives us plus or minus I as roots. And you steal the complex plus or minus I, steal one of them. You look at that, a plus bi, in this case, is 0 plus 1i. And so you make up e to the 0 x times cosine of 1x and e to the 0x times sine of 1x, because come out cosine and sine, we know that. Okay, that was example 1. The idea was to show you that you get power series, and in that example, the power series are recognizable as cosine and sine. All right. Example 2 and example 3 are the same differential equation called Airy's equation. Now, when you look at the book, the authors the authors at the bottom, they tell you about Airy's. I'm in the wrong section, I see, when I look down here. They have a thing about Airy at the bottom, and his name was Sir George Biddle Harry. That was the guy. And it occurred to me this morning, his first name could have been Sir. I wonder if anybody in Britain ever names their kids Sir, so that they sound like nobility. Just occurred to me. I had a realtor when my wife and I were looking at a house a long time ago, looking for a house. Somebody who introduced us to the realtor said my name was Dr. Brady. I never insist on the doctor, okay? The realtor thought my name was Doctorbrady. In other words, they didn't think it was a title, they thought that was part of my name. So in that realtor, I will always be Mr. Dr. Brady. And so when I read Sir so-and-so area here, I thought, that'd be interesting. Name your kid Sir somebody, and sounds like, there was a movie about 25 years ago, a Western movie, where the killer was named Nobody. And it was kind of a spoof on Westerns. And so when somebody was murdered, they say, who did it? And they said, nobody did it. And of course, misled people in terms of who did it. Okay. Anyway, I'm weird this way, okay? I'm sorry. So I think about Sir, and I wonder if anybody in the United States names anybody doctor. They go through life, hi doctor, and everybody else thinks, Okay, well, enough of that nonsense. So what's the difference? Well, it's almost like the one we studied already. It's not quite. Now, the trouble with this one is you can't do what we did in the last chapter because the coefficients are not constants. One of them is and one of them is not. Okay? Now, this is going to be, by the way, a study of more general stuff. And so I'm going to write down that at the top up here and leave that alone a little while. What we're going to study in this chapter is a more general thing than we studied in the last chapter. And we can have homogeneous ones like this. We can have non-homogeneous ones. That's another problem. But we're going to call now things in this chapter capital P, capital Q, and capital R. This particular problem, the capital P is 1, and the capital Q is 0, and the capital R is minus X. But please, it makes no sense to do this because this only works with constant coefficients. Therefore, unlike example 1, we can't write down 2 answers and then give an example of where we have series that show you what the answers are. It isn't that simple this time, even though this is a really simple equation. Now, example 2, x naught is 0. In example 3, x naught is 1. And so what this section's about is to do 3 problems where you stick functions and the first and second derivatives as power series into the differential equation and try to solve it. Meaning you try to find not these things, you try to find these things. All right, and usually we'll get some equation that relates the 10th one to the 5th one, or the 10th one to the 9th one, or something. We'll get what's called recursion, okay? Because when we have initial conditions, we will know what the first 2 are. When I have, I guess I erased it, when I have initial conditions, we know what A naught is and we know what A1 is, okay? Why do I know what A naught is if I know the answer here? If I put x equals x naught in here, all of these wipe out. And so whatever the answer is, y of x equals here, if I put 0 in, I get A naught. Okay, that's like an initial condition. And if I differentiate one time, I will get A1. when I stick in zero, x naught or zero, okay? So what do I do here? Well, same game, I'm gonna do it over here. Y of x, I'm gonna assume, you want to call it something else if we want, is a naught plus the sum from 1 to infinity of ak. Now, if x naught is 0, then it's x to the k. Okay? First derivative is going to be, and you have to do this, you'll have to get used to this, and what you might do is write it down someplace once and then just copy it all the time. It's the same derivative except it's k, ak, x to the k minus 1. You need to practice this a little bit. And then we usually like to write this as kth powers. I talked the other day about the problem with the 0 power, so I'm going to get off of that. But I like to write it like this, and when you do this, it takes a couple of steps. Okay, so far I haven't changed the meaning of the index, so it's still a k, ak, x, but to the k minus 1. All I've done by doing this is to take away the 0 power idea. So everything else from 2 to infinity is a power of x. And now I want to shift, and so I'd write this as a1. I'll shift the k back to 1. That changes everybody else up 1. And so the subscript is up 1 and there's x to the k. So you need to do that a couple of times until you understand that idea. We don't always shift it back. It depends on how complicated the equation is, as you're going to see in a minute. I need to figure y double prime. I will take the last thing I did. It's going to be the sum from 1 to infinity of k plus 1 a sub k plus 1 x to the k. When I differentiate though, and that's what the expression is. If I differentiate it, I will get k plus 1 k times a sub k plus 1 x to the k minus 1. Because when you differentiate this, you get to k plus 1 again. When I do the x to the k, I get k out in front. Same a sub thing and 1 power less. And again, now I'm going to take care of the problem by splitting off the next term. The next term is when k is 1. I'll get 2 a sub 2 x to the 0. And my problem is always in this class with the way we're doing this pandemic is I always run out of space. So I have 2 to infinity, k plus 1 k is copied, a sub k plus 1 x to the k minus 1. Then if I shift that again, I'll have 2a2 plus the sum from 1 to infinity, k plus 2, k plus 1, a sub k plus 2 x to the k. Now, I don't want to do that too many times. It just takes too long. This is what you might do a couple of times and save it somewhere. That's why I'm doing it in a different place. Okay, because I want to substitute stuff into this second derivative and into the y. Now, if I take the original y, that was a sub 0 plus the sum from 1 to infinity a sub k x to the k.
Dr. Brady.
Yes, just a second.
Okay.
Yes.
The summation on the very bottom of the right side,
This one?
it's all kind of blurring together. Could you
Okay.
write that a bit larger?
I'll rewrite it somewhere.
Okay. Thank you.
I think we have those. Y is going to be the same all the time. So let me, as I say, someplace you write down. And I'm going to write down the last one, although sometimes you don't do that. And we'll talk about that in a second. That's the purpose of doing all this, is to talk about it. So I hope I haven't made a mistake in kind of doing this fast. Is that better up in the top here? Can you see that a little better?
Yes. Yeah. Sorry.
Better than the other one. I don't write very well anyway. When you're old, you find out. You'll find that out.
Yeah, I can see that better.
Okay. Now, what I wrote here was minus x times the y part. And I wrote this was splitting out to a naught. If you don't do that, this would be the sum from 0 to infinity, where you'd make sure you remember that x to the 0 is not 1. I mean, it is 1, but it's not really that symbolism. We talked about all that the other day. Okay, what do I do with x with y double? Well, this one I just copied, maybe that's what I use, because I want to talk about powers x to the k. So I'd probably copy that one down here. So because of my space, let's suppose that, and also you guys don't see it at the bottom, let's suppose I copy it down there. Okay, so we've got 2a2 plus the sum here minus x here. Now, the x here, it's not part of the power series. What I'm going to do is I'm going to take the x and multiply it in here. Okay, so in this particular problem, I don't have to alter the y double. When I've done that generic thing I told you to do over here, I can copy that down right here. The problem in this problem, this example, is not the y double prime, because I've already got it to the power x to the k here. So I have a constant, I have a power of x, I have a power of x squared, I've got a whole series. But this next thing is a problem, because I have a series, but I have a times x. So I'm going to have to rewrite that one by saying minus a naught x and minus k from 1 to infinity a sub k x to the k plus 1. Because when I multiply x times x to the k, I get x to the k plus 1. So if you look at the thing here, this is kth power from 1 to infinity. This is k plus first power from 1 to infinity. I can't just add those together. I'm going to have to adjust this one to make kth power. So it's minus a sub 0 x, okay, minus, all right, I'm going to change to bring the x to the k plus 1 down to x to the k, I'm going to have to increase, let's see, I got to do this right. If I increase the meaning of the index, then I decrease the meaning over here. So I make this k equals 2 to infinity. And what do I have to do? I've got to bring everybody else down. So by increasing the index, I have to decrease the meaning of the things over here. So k becomes k minus 1 and k plus 1 becomes k. All right, now that was just playing with the second thing. So if I write it all down now, hopefully maybe in this space and so you guys can see it, is 2a2 plus this sum, and I'm just repeating this now, k plus 2, k plus 1, a sub k plus 2, x to the k. Now, minus a sub 0 x and minus the sum from 2 to infinity, a sub k minus 1 x to the k. Okay, now I look at that and I'm happy that everything is x to the k. But I'm unhappy because one of them starts at k equals 1 and the other one starts at k equals 2. So I can't combine them. Now, we also hope that I'm not making any dumb mistakes. You've got to do this carefully. I think I am, but I'm very capable of making little dumb mistakes. And so you've got to keep checking this stuff. Well, let's assume for the moment I haven't made any mistakes. Okay. And what am I going to do? Well, I got x to the k. I don't want to change the meaning of the subscript because that will alter the k. What I want to do is take one off of the k equals 1. So I write this as 2a2 plus let k equal 1, and I will get 3 times 2, so I'll get 6 a sub 3 x and plus, I'm sorry, x to the just 1 plus the sum from 2 to infinity. And as usual, I have a little space problem. So that's going to be k plus 2, k plus 1, a sub k plus 2. And I'm going to put this other part in here, minus ak minus 1, x to the k. And over here, I'm going to put minus a naught x. So assuming you have this all written down somewhere, or we'll access it later, this is what we get, I think. And that's all equal to 0 at the end. And so what I get is 2a2 plus 6a3 minus a naught x plus a sum from 2 to infinity of k plus 2, k plus 1, a sub k plus 2 minus a sub k minus 1, x to the k equals 0. Now, at this moment, I don't care if that's right or not, because part of what we're trying to do is to show you how to do it. And if I didn't make any dumb mistakes, then I've got what I want. Okay? If there's a dumb mistake made somewhere, then there's some place where 6 is wrong, or the A3 is wrong, or something's wrong, and I'm not going to come up with the answer that's written in example 2. But what I suggest you guys do is don't look at example 2 in terms, and look at it, but to practice, do this on your own like I'm doing it right now. You should come up with the same thing the book comes up with. All right? And if you don't try to find your mistake, do it again. If you make a dumb mistake, sometimes they're hard to find. If you do it twice, you're unlikely to make the same dumb mistake twice. You might make a different dumb mistake, but it's probably not going to be the same one. And then you can compare stuff to see like, oh, I put a minus where I should have had a plus or something. Okay, but it's hard to find when you just have this mess. All right, so assuming I didn't make a mistake, for me, the solution that I'm going to turn in for my test, I'm going to say, okay, what do we know about A2? Now, remember that when I say a power series is 0, it is identically 0. I'm writing a bunch of minuses. That means every coefficient of any power is 0. So if I have 2A2 here, I'll sit in here by itself, A2 has to be 0. A2 is 0. It's the only thing it can possibly be. Because this whole left-hand side thing is exactly 0 for every x. And therefore, has to be 0. And A3 will have to be A0 over 6. If I didn't make any mistakes. And AK plus 2 will be K plus, wrong thing, AK minus 1 over K plus 2 times K plus 1. Why? Because this coefficient has to be 0. And what you always should do is say where that is. This is for K greater than or equal to 2, because that's what this was. And if I didn't make any mistakes, now I try to figure out what all the coefficients are based on the information I have now obtained. Okay? Now, this is K plus 2, and this is K minus 1. So let's just take a little bit. Suppose K is 2, because 2 is the first thing K can be. If K is 2, I get A4 is A2 minus 1 is 1, and K is 2, so I get 4 times 3. So A4 is A1 over 4 times 3. Now, don't make it 12 yet. Leave it alone, because remember, in general, with these things, there are factorials involved. And so when I see 4 times 3, that might be part of a factorial later. It might not, I don't know. But if I make it 12, I lose that thought. Okay? And notice here I had a 6. I wrote 6 because I had 6 from sticking stuff in, and I went ahead and made 6. That's also 3 factorial. Maybe that will be what I need, but 6 is 6, and I hope you know enough to say 6 is 3 factorial if you had to. I don't know if you know 4 factorial is 24, and 5 factorial is 120, and 6 factorial is 720, and 8. I don't know if you know that, but you do this long enough, you will. And when you get some numbers, you'll realize, oh, 8's missing, or 2's missing, or something. Okay, when you get 12, you think that's half of 4 factorial. You haven't been thinking that way. But life is always changing. So now what I notice about this, besides is 4 and 1, they're 3 off. What's 5 going to be? A sub 5, that's when k is 3. A sub 5 is a sub 2, because 3 minus 1 is 2, over 5 times 4. But a sub 2 is 0. So a sub 5 is 0. And what do you think a sub 8 is going to be? A sub 8 is going to be when k is 6. That's like a sub 5 over something, but a sub 5 is 0. So I get a sub 2, a sub 5, a sub 8, a sub 11, because humans like patterns. So what I need to figure out is how do I write 2, 5, 8, and 11, and so on in a pattern? Well, that's every 3. So 2 is 3 times 1 minus 1. 5 is 3 times 2 minus 1. 8 is 3 times 3 minus 1. Now, I'm hoping, I don't know, maybe I can erase the top part up here. Okay, so what I have is a sub, what we said, a sub 2, 5, 8, a sub, we said is k, if k is a multiple, so if k equals 3 times n minus 1. So, and so I won't write k. If I write a3n minus 1 here is 0, does that work? In other words, if n is 1, I get 2. If n is 2, I get 5. I think that works. So this would be for all n greater than or equal to 1. Now, that is in a certain sense, 1/3 of all the coefficients is an infinite number of them. 2, 5, 8, 11, and so on. That wipes out about 1/3 of the ones I want to find out. Okay? Now, because of this representation right here, what about a sub 3? A sub 3, we figured if k is 1 here, that doesn't work the formula. That's where we did this one. So this didn't come from that formula. Could it have come from that formula? Is this one so suppose, now from the differential equation, because of the way I split stuff off, I split off something here, but let's look, if k is 1, now it's not supposed to be the formula, I'm just playing now. If k is 1, I get a3 here, I would get a0 here, and I get 3 times 2. Yes? So because of the way I did it, it split one of them off. If you do it a little differently, you might come up with this one as part of this one, but if I change this to 1, because this is true, it's the same formula. Okay, so whether I do that or not, the point is, what's a sub 6? A sub 6 will be when k is 4. And a sub 6 will be a sub 3, boom, over 6 times 5. So I'm out of space, okay? A sub 6 will be a sub 3 over 6 times 5, but a sub 3 is a sub 0 over 6 times 5 times 3 times 2. I'm missing 4. I can't write this as a factorial, but it's almost a factorial. Now, because of our time, it's 17 after. When you look at example 2, it's on page 200. Okay, you will see that the coefficients of the ones like 3, 6, 9, 12, and so on, they have denominators 2, 3, 5, 6, 8, 9. In other words, 2, 3, you skip to 4. 5, 6, you skip to 7. 8, 9, you skip to 10. Humans see patterns. At least this human sees a pattern. And so you write down 2 patterns, or 3 patterns. 2, 5, a sub 2, 5, 8, 11, so on is 0. That's one pattern. Then a sub 0, a sub 3, a sub 6, a sub 9, that's the second pattern. And a sub 1, a sub 4, a sub 7 is a third pattern. Now, because it's 17 after, let's just talk about what are we looking for? We're looking for 2 linearly independent solutions, just like the last chapter, right? Okay. Well, I've got 2. What I do is I split off the powers 3, 6, 9, 12. In other words, in the power series that I'm trying to do here. And so I'm not going to have time to use this again, so I'll just erase it. What I'm going to do is split off into 2 power series. This one's going to be the a sub 0, a sub 3, a sub 6, and so on. This is going to be a sub 1, a sub 4, a sub 7, and so on. Meaning I need to write down here, this is going to be a, what's 1 and 4 and so on? That's 3n minus 2. If I do n now, put infinity top, don't know what this is going to be yet. A sub 3n minus 2. Okay. And over here, it's 0, so forth. This is a sub 3n. If I do a 0 and don't split it off, it's going to be n equals 0 to infinity. Because I do that, that'll give me 3, 0, 3, 6, 9, and so on. Here I'll get these things. So what I'm basically doing is splitting the answer up into 2 pieces. The third piece is when it's 2, 5, and so on, but those are gone. All right. So I'm thinking of splitting the original series up into 2 pieces, and one of, in other words, when I write down what a sub 3n's are, that's coming from this recursion. I will have a separate, okay, I'm going to have an infinite thing here. When I do this, whenever I find out what a sub 3n is here, which I have right over there, this is one series. This is the 1, 2, 3, 5, 6, or whatever I said, 8, 9 in the denominator, if you remember a minute ago. Anyway, I have 2 series. I'm looking for 2 series because I'm looking for 2 independent answers. Now, our time is gone, but how do you prove they're independent? You do their Wronskian. This is now, we would need to do a Wronskian of 2 power series. But it turns out that's not bad, because we're going to stick in the x naught. Remember when you do a Wronskian at a particular point? When you do a Wronskian at a particular point, most of these things in the power series are going to go out. And so you can actually show in example 2 that the 2 things you get are linearly independent. Now, okay, it's 21 after. I'm gonna cut off the recording by 1.